Good evening, everyone. Thank you for joining. My name is Kishore Reddypalli. I manage data platform engineering at Salesforce. In this talk, we're going to talk about our ingestion pipeline services, along with my colleague, Dino. He's the lead engineer in the team. So with that, let's get into the presentation.
Thanks. Yeah.
Okay. So we are Salesforce. For the starters, Salesforce is a cloud-based CRM platform enabling businesses globally to sell, service, and market their products to the customers in a very innovative way. And so recently, with Slack and Tableau, it was becoming more like a data company and providing a much richer collaboration tools for the customers. So what we do at Salesforce, we are building our next generation data platform, which we call it as Unified Intelligence Platform, in short UIP. And UIP is a one-stop destination for all Salesforce teams. So it's an internal data platform for Salesforce. And all the Salesforce business teams comes to this platform to access the data sets, to understand their business areas better and improve their business areas. And Salesforce and UIP is a modern, trusted, turnkey environment that can enable analytics and ML on big data sets. And UIP drives enormous value to Salesforce, avoiding like siloed data usage, enabling various business functions like security, observability, and monitoring, and product usage analytics, et cetera. So what does UIP consist of? So UIP is a bunch of technologies. At the core, we use S3 to store our data sets. It's around like 100 petabytes of data that we have today, and it is growing enormously. And we have like various data lake engines, like Spark and Trino. We use Spark for our ingestion services, which we're going to talk about that in a minute. And we use Trino for our query services. And we use Hive as our metastore. And we have various other technologies like Elation for data discovery. We use notebooks for our interactive exploratory analysis for data scientists and data analysts. And we also enable Airflow for data engineers to schedule and orchestrate the workflows. So coming to the ingestion, which is the core topic of this session, so we have like around 100 petabytes of data. For bringing in these data sets, we get like around 1 trillion events per day and multiple terabytes within minutes. And the most interesting part is when the data comes, all these data sets are of different event types, and it has its own schema. That is the most challenging part. So how does the data flows into our UIP ecosystem? So all these data sets in Salesforce clouds, if you are using it, like all these data sets flows into a common cluster called Kafka. And Kafka cluster drops the data into our landing buckets. And we pick up the data sets from that landing bucket, and we process the data and write the data in a columnar format so that the users can query the data efficiently for analytics. So if you look at like in the diagram, if all these data sets that get landed is more of a raw format rather than columnar format. So our goal is to convert that into a columnar format and make it accessible through Spark and Trino services. So that's great. Like this is how like the data gets landed into the UIP ecosystem. But what happens under the hood when we are actually ingesting the data sets? So when the data comes in, all these data sets are various event types, I can put it as. And each event type has its own schema. And when we get the data, it's all mixed in one single file. And we'll get like thousands of files that we get. And our goal is to go and demultiplex all those event types, because that is how our query patterns work for the users, so that they can run the analytics on that respective event type. So our heavy compute function happens demultiplexing those event types into a separate thing, which is color-coded here, and apply the schema for that respective event type, and process the data, write it in Parquet format, and able to query the data as a separate table for each of this event type. So if you look at a high level, you get like mixed set of records as an input, which are in Avro format. And in the output, you have the Parquet format with which we have written in G standard compression for better storage footprint. And it is all partitioned by batch ID, date, and hour. And this is the most interesting thing, which is to process all this data, we need to be cost efficient. And also, we want to be processing these data sets within 10 minutes latency. That is our data freshness requirements. And applying the schema and exploding the columns is the most challenging part for us. So if I go deeper into the challenges in the implementation, if you look at, we get like around this 10,000s of files, and loading the data sets itself it takes a longer time. And the data is also skewed, because each event type has a different volume of data that comes in. So we need to balance the cluster accordingly and process it. So this is, with that, like I would let Dino speak to how we solve this problem of the challenges that we have.
Sure. I just use this. Yeah, when Kishore just assigned me this task, I say, yeah, it's a few lines of code, right? You just reading all these files, and then you read this arrow, first read from the SQS, bring these 40 key files in, and read with arrow, and then filter by each logger, each event type, and then write it out. So what's all the files, right? So if I would say that if we have listened to all these sessions, it's all like our engineering world is engineering life is getting much better, right? It's kind of a click and things just works. But it's that when the devil always hiding in the details. So first, when you're reading these 40 key files, it takes minutes. We have a 10 minutes latency. When you're reading the data, it already takes 3 minutes. So it doesn't work. So then the data is really skewed. And if you partition it, then the partition will really screwed. And you cannot just write it out, because one event type will take more than 10 minutes. You cannot really meet our expectation. It's so screwed that, yeah, so like to give you some context, like we have, for each 5 minutes, we process around 2,000 event types. But the top 10 event type will occupy around more than 15% of the data volume. So yeah, so why we cannot just read with this arrow? It doesn't work because it's too slow. Because when you're reading this, use this API to read the arrow file, we'll first need to build the in-memory index. That is a very costly process. And then we think maybe we can just use the low-level API, just use the RDD API. Then we come down to this DStream, smart DStream. Then it's pretty much we manually reading all the files and create this sequence of RDDs. This speed up things for minutes. Now we come down to 10 to 30 seconds. And also, when we using streaming, it also get us the benefit that we amortize the Spark application startup, the setup cost, because we need to support 2,000 executors in the same time. So this just a piece of code that we actually just use AWS SDK to read in all these files instead of using the Spark API. So now it's good. You read in all these files. So what's the next step is, so you have all these files, all mixed event record types. Now you need to do this big shuffle to split them into event type partitions. And remember, there's all this DScrew thing, right? So we have to do, it's the common practice. We need to use sort to make the partitions more evenly distributed. The good thing here is we observe the attribute that for each log line, the size of log line is not really varies a lot. So, but the disk size for each log record type may change a lot. So what we have done is, okay, we from the history, we do some statistics, and we know that each log record type, how much records can consist of units, like 128 megabytes. So then with these stats, then we can evenly distribute the partitions. Because when we read in the log type, we also read in, have the partition count already calculated along. So basically, we'll also amortize that cost into the reading. So now with this graph now we have, let's assume we already partition evenly in memory. What's the next step? We have more than 2,000 event types. We now need to write it to per key. The problem is with RDD API, we cannot write per key. We have to get back to the DStream API. Now Spark can let us do, you can submit a Spark job within thread, with thread. Now we need to create 2,000 threads. So this is not a typical job. That's why we want to share here, is also because although it's not really a typical use case, but it can apply, this scenario might apply to your use case also. So the really speed things up, or the optimization here, is that when we do this range partitioner, so Spark can do a hash partition and a range partitioner. With hash partition, it's hard to get from this. If we look at this graph, now we have this giant RDD in memory. We want to grab a portion of this belongs to one event type and then write it out. So if we use the hash partition, then in my one event type might fall into different partitions. So when we write out, we have to do filtering. So with range partition, we don't really need to do this partition. The good attribute of range partitioner is that for each key, it will ensure you that each key will fall into its own partition. And then another optimization here is that when range partitioner, how range partitioner works is you need to first example the RDD. And this example, first is inaccurate because it's sampling, right? And also because the data is so skewed, so if you sample too much, it takes too long. If you sample too small, the sampling is so inaccurate that one event type will just occupy the whole time. So what we did is that when we read in all this data, we know exact distribution. So we create a mocked RDD. Then we just tell this range partitioner, okay, this is the distribution, just sample, don't do any sampling, just do it. So this reduced the range creating this range partitioner from 3 minutes to within 1 second, you can get this range partitioner. Okay, next is, we're talking about schema management. Earlier we talked about, so the uniqueness of our problem is that we need to apply different schema for each event type, and each event type has its own table in Metastore. So how do we now, since we are in a streaming context, so how do we, the schema also evolved every day, so how do we keep the schema updated, and how do we distribute all these schemas to each executor? So I think this we just employed the common used patterns, kind of. So we use this transient lazy var and also use the guava loading catch to make this work. And we refresh the catch every hour so that the schema, even you update it, it won't be older than 1 hour. Earlier we talked about now, so from the beginning of the batch, you kind of reading in 40K of files, and then you kind of trying to write out all these 20,000 log record type, the event type. Now the problem is that it will create a bootstrap situation. Just like every morning you start up, everybody get into the office and start up the computer, and it will create a huge storm for the backend. It's the same thing. So in the batch, when the batch started, so it will create this 2,000 event type job to write out the Spark job. Then it's also slows down the Spark. The Spark scheduling is kind of very limited there. So what we do is we're kind of trying to slow down our submission. So since we have 10 minutes, we're trying to schedule to schedule our partition so that the partition can be write out within 5 minutes. Thus, we can spread our job submission so that as long as it still have the time to write it out, we're good. So the Spark scheduler can have time to schedule the job. And another optimization here is when we actually need to write multiple copy of data. So we want this job to finish before new jobs comes in. So what we want to do is we limit the concurrency here. So we pretty much just we kind of calculate how much cores this job need to use, and then only submit the new job after results are released. And so we also size the partition based on the processing time. So that, again, there's some large event types that will write, just in one local type, we will write 100 gigabytes of data out. So we need to kind of spread this into multiple partitions, how to size their partition. If you are size too small, it will use too many cores. And if you size too large, then the latency will go up. So that is, we kind of sizing the partition so that it can process around 5 minutes. So this is a pretty typical computer science problem. This is called identical machine scheduling problem. So you kind of get a optimized solution just by sizing the, it kind of make your job more unit. It's kind of a job unit is a kind of normalized unit for your job. So there's also this late arriving data. So what is the late arriving data problem we're dealing with? So on the source, when the data comes into Kafka, it's partitioned by machines because it's naturally there's data center and there's which machine has which cluster sending in these data, right? So it's the topic in Kafka is partitioned by the machines. But in when we query the data, most analysts want the data to be partitioned by time and also by the event type. So if there's late arriving data, meaning if one machine sending some data spread like days ago, then for this one specific machine will create thousands of, might double our partitions. So that is a huge problem for us. So we have done two things to make this problem contained. One is we do some in-memory compression. So we consolidate the data for several hours into this one partition. And then for the long period, if it's deleted by date, we kind of divert the source so that we can accumulate or buffer the late arriving data and reprocess it in one batch instead of spread into multiple batch. And since we are living in the cloud world, a lot of things need to be considered in this cloud environment. With our volume, actually, a lot of things I never know before we really get into this volume. So since we are writing 2,000 partition event types, and that's around more than 1.2 terabytes of data, and then you will hit all this 503 error if you don't optimize for the cloud. So these are a few optimization need to be considered. Is make sure you use the EMR S3 committer, and the S3 is also prefix randomized because S3 is its distribution is based on the prefix. So it's counter to our intuitive. Usually we want to partition the data by date, then by hour. But this way, all the date will, for this hour, write into same prefix. So that will create when you query the data, you will create a storm for the S3, and you will get all these 503 deny server thing. So, and also, because we have these 2,000, sometimes with 2 or more clusters, you got thousands of executors trying to listing at the same time. That is also won't work because the listing API has more limitation than the read and write API. So that's also something we learned. And of course, EMR is something really costly. We also need to, we have done some cost optimization by using support instance. And we also, because this log is also seasonal by nature, so we will do, like during the night, we will have less resource allocated, and during the weekend, we also allocate less resource. This is something, with all the optimization, we kind of can deliver. Our goal is P90, 10 minutes. Yeah, so this is some Graph dashboard to demonstrate our work. With that, I think that's what we have. Thank you. Any questions?
What do you use to cache all of your partitions?
Cache?
Cache.
You use to cache. So you mentioned you cache your, all the randomized salted prefixes, right? Listing those is bad. What do you use to cache that?
Oh, we don't cache. We hash. I mean, randomize the prefix.
So you do listing calls though in order to discover.
You mean that one? That one is we're pretty much we list we use the driver to list that partition, all the files in that directory, and create a cache for this directory, right? So it's pretty much, then all the executors just read this cache file instead of doing the listing.
So it's almost like a broadcast, but you have your own system set up to do that. Okay, thanks.
All right, any more questions? And then I have one question. What is the cluster size that you are using in production?
Class size?
Yeah.
We actually, so we, 5 minutes batch, right? We need 10 minutes to process it. We need 2 clusters. That means, right? So for each cluster, we have 125 nodes. That's M524X. So it's a really large cluster. When we are at this scale, a lot of problems will pop up, like the EMR monitoring doesn't work at this scale. So a lot of the dashboard won't work. So we have to write our own tools to do that. Yeah.
All right, thanks. All right, with that, thank you, Kishore and Dino, for the great presentation.
Cool. Thank you.
Thank you.